Hello, welcome to AISSMS Institute of Information Technology. I, Sagar Jagtap, Assistant Professor, Department of Instrumentation Engineering. In this video, we will see the concept of deadlock. The objectives and outcomes. The objectives are to describe the concept of deadlock, to explore the handling of deadlock, to give an overview of deadlock prevention. After the concept of deadlock, student will be understand the concept of deadlock, detection of the deadlock, and how the recovery from the deadlock. The deadlock problem. A set of lock processes, each holding resources and waiting to acquire a resource held by the another process in the set, so that no one process can be able to execute. This example can be illustrated as, suppose a system has two tape drivers and there are the two processes P1 and P2. Each process hold one tape driver and is waiting for the another tape driver. So in this case there are only the two tape drivers, and this both the tape drivers are held by the process P1 and P2, but they are now waiting to get another tape driver. Here the process P1 and P2 does not release their tape driver to meet the need condition. Pictorially we can see this by the bridge crossing example. Here the bridge is resources. Two vehicles are come each other face to face, so that all our traffic is get deadlock. Deadlock characterizations. The mutual exclusion. Only one process at a time can use a resource. Hold and wait. A process holding at least one resource is waiting to acquire additional resources held by other process. No preemption. A resource can be released only voluntarily by the process holding it, after that process has completed its task. Circular wait. There is a set exists where the processes are circularly waiting to release the resources. In deadlock, the knowledge of the resource allocation graph is very important. So this graph contains the set of vertices V and the edges E. If we see this process is represented by this circle, then the resource type with 4 instances is represented by this square. Inside the square there are the small 4 square which represent the instances. So Pi is a request instant of Rj, which is directed the arrows from this process Pi to the Rj. Suppose Pi is holding an instant of Rj, which is represented as this arrow from the resource instance to the Pi. Here, if a graph contains no cycle, then there is no deadlock. If graph contains a cycle, then their chances of the deadlock are not deadlock. Here, if only one instance per resource type, then deadlock. Second, if several instances for resource type, then the possibility of deadlock. Now if we see this graph, in this resource allocation graph, there is one cycle is formed, but there is no deadlock, because if we see this resource R2, there are the two instances, and these two instances is acquired by the process P1 and the process P2. So the graph with one cycle, but there is no deadlock. If we see this second example, here there is one cycle is there. Suppose this P1, R1, P2 and R2. If we check this R2, here in this R2 resource there are the two instances, that instances are acquired by the process P1 and the process P2. But if we see here, the process P3 is also asking for the resource R2, instances R2. So there is a cycle is formed. So here deadlock is occurred. So here graph with a deadlock. Now if we see this third diagram, then there is also cycle is occurred, but here no deadlock is there. Now deadlock prevention. The deadlock can be prevention by the mutual exclusion, hold and wait, and circular wait. No preemption. So deadlock avoidance. So to avoid the deadlock requires that the system has some additional prior information available. The simplest and most useful required for to avoid the deadlock is that we have to run the system into the unsafe phase. This is one of the physical example of the deadlock, which is the traffic deadlock. Thank you.